Hi, good day all. Welcome to Chapter 2 of our Practical Finance course. Today we're going to talk about formulas. Please stay tuned. Yes, we're going to see some finance formulas, especially those that we need for building our business cases. But I'm not just going to show you the formulas, we're going to derive them so you can know and understand where do they come from and what do they really mean. The first formula we're going to look at is the simple interest formula. That is, the amount of money we gain at the bank or another investment product in terms of interest. At the end, you're going to see that all formulas we covered here come from this simple formula. So if we have $1,000 at an investment that yields 5% a year, at the end of the year, we should have 5% of that $1,000, that is $50. So at the end, we will have $1,050. Okay, so what is the formula that we just used? Okay, so this is the formula we used. As you see, a future value is our principal plus whatever the principal gain in interest. So here's where the 5% was, and here's the principal. The $1,000 times 5% is $50. And then the $1,000 we began with adds to that $50, and we get the future value of $1,050. And that can be reduced into this, taking common factor, the present value or the principal, and we get this formula for the future value after 1 year of interest. But what happens when we have more years, 2 years, 3 years? Well, the formula multiplies by n that amount of interest. So we have the same formula multiplied by n here. So that means if we reduce it, that our simple interest formula is this one. So let's see an example. If we have an investment of $1,000 at 5% a year for 10 years, this is how we calculate it. See, we have this $1,000 times 1 plus 5% times 10 years, which is the same as 1 plus 5 over 100 times 10, which is the same as 1 plus 5 over 10, which is 1.5. So we have to multiply 1,000 by 1.5, so our future value is $1,500. At the end of the year 10, we would have $1,500 at simple interest rate. The thing is that neither the bank nor any other investment options pays you at the simple interest. They pay you at the compound interest. That's the formula we're going to see next. Okay, let's begin with the formula we already know. This formula calculates the future value of a principal after 1 year at an interest rate. So what happens after that first year? After that first year, let's see the example we just did. This $1,000 transforms into $1,050, 1 year. After 2 years, we should then use this $1,050 as the new principal and calculate again the 5% we gain. So we'll obtain $1,102 with 50 cents. This $1,102.50 should be the principal for our third calculation of interest rate. And here it is. So we have this times the new 5%, and we obtain $1,157.62. That is the future value of our third year. That should be the principal of the fourth, and so on. If we do that until the year 10, which is our previous example, we will have something like this, where this principal is the end of year 9. Then we apply that to the 5%, and we will get this $1,628.89. See how different it is from the $1,500 we just calculated at the simple interest formula? Imagine if the interest rate is higher or the number of periods is higher. The results will be much different. Okay, so let's do this instead of numbers with letters. So we have the future value of our first year. It's our principal times the interest after this first year. So the second year we need to use this as a principal, this future value of the first year as the principal, and we do again the calculation of 1 plus I. And this future value 1 is exactly this one over here. Is the principal times 1 plus I. So if we do that, we obtain the principal times 1 plus I times 1 plus I again. So it's a 1 plus I squared. Thus, the final value or the future value after 2 years. When we do that in the third year, we will use this present value times 1 plus I squared as the base value or the principal value of our third year calculation. So we have 1 plus I squared times present value right here, which transforms then to 1 plus I squared times 1 plus I, which at the end is going to be present value times 1 plus I cubed. And we will continue on and on until the n number of years is reached. And that is the formula we're looking for. The composite interest rate formula, which is here. And from this formula, as I told you, we're going to derive every other formula. First, we're going to derive the present value formula, which is right here. If the present value is here, we just clear it out. So the present value is then the future value or the future cash flow of an n period divided by 1 plus I to the n. Another important formula we need to know when building business cases is a formula that converts annual interest rates into monthly interest rates. And that is because normally the discount rates or interest rates are given in annual terms. And the business cases we used to do are made in monthly terms. And no, it's not dividing by 12. Let's see how we do this. Okay, we know that by the end of a year, the formula we already know of future value is the principal times 1 plus interest to the 1, because it's 1 year. And that interest is a year interest. And that will be the same if we do it by 12 terms, which is this one over here, but with the interest being a monthly interest. So if both formulas are the same, they reach the same future value at the end of 1 year, then these two terms must be the same. So if these two terms are the same, then we obtain that 1 plus the interest of 1 year to the 1 is the same that 1 plus the monthly interest to the 12th. Then if we take the 12th root in both sides, this cancels out and we get the formula 1 plus im, that is the 12th root of 1 plus I sub y, which transforms into the formula we were looking for. The monthly interest equals the 12th root of 1 plus the yearly interest, all that minus 1. Or we can clear the yearly interest if we have the monthly interest, and it's very simple. It's 1 plus I sub m to the 12th, all that minus 1. So these two formulas we're going to need very much when building business cases, so please keep them in mind. Okay, our next formula is the net present value formula. And the net present value, as we defined on our last chapter, is just the sum of all present values of all cash flows of the project brought to the present and sum. We need to add all the present values of each of the cash flows, and then that is the net present value, including, of course, the initial investment, which is placed at the period 0. So here's the formula. The net present value is then the sum from 0, which is the initial investment, to m number of periods of each of the cash flows divided by 1 plus I to the n, the index of the sum. Okay, the multiplier formula. Here's a funny story. When I started working in finance, I encountered lots of problems where all cash flows have the same amount in every period. For example, the monthly access fee of a particular telephone plan, I would like to find its profitability in the average customer life, which I think it was around 48 months or so. Okay, so I was wondering if there was a factor I could use to multiply this access fee with, so I could have the net present value instead of adding up all present values of all 48 access fees. I knew I had to multiply by something, of course not 48, because I knew there was a deflection factor due to the discount rate. So it was a factor that had to do with the discount rate and the number of periods. But how to calculate it? So I had to pull out my college math, and here is how I did it. Okay, so I wanted to get this sum, right? Where SPV stands for the sum of present values. And here you have all cash flows which are constant in their nominal values. We call it FVs. And they are brought to present by these present value formulas. And then we need to add them up. That is like the net present value. But if you notice, we're not considering the initial investment. We are beginning with the first month or the first period. But if you watch closely, you will see that to get from one term to the next, you need to multiply it by 1 divided by 1 plus I. As you see, this one over here is square. So it's like multiplying this one by 1 over 1 plus I. So is this one, so is the next one, etc. So it is actually a sum of a geometric series. And we know the sum of a geometric series with a particular common ratio, which in this case is 1 over 1 plus I. So we have a sum of a standard geometric series, like this one, where A is the common factor in every term, and R is actually the common ratio. So to get from one to the other, you need to multiply by this common ratio, AR, then AR squared, AR cubed, etc. So math tells us that to get the sum of this, we need to apply a trick, and that is to multiply this same equation by R. Here it is. So R times S sub n, which is the sum we need to calculate. Then we have here AR squared, because we multiply it by R, AR cubed, and to AR to n plus 1, which is the last term. So if we subtract these two formulas, the previous one and the one we just got multiplying by R, we see that all these terms cancel out. So we end up with this first term here and this last term here in the right side, and in the left side we just have S sub n minus R times S sub n. So here it is, S sub n minus R times S sub n is A times R minus A times R to the n plus 1, which we can contract taking common factor in the left side S sub n times 1 minus R, and in the right side A times R multiplied by 1 minus A times R to the n. If we then clear S sub n, which is the one I wanted to calculate, that is A times R times 1 minus A times R to the n, all that divided by 1 minus R. So let's remember what R was. In our formula, R was 1 divided by 1 plus I. A is actually the constant cash flows, or the constant future values, and n, of course, the number of periods, that I think we call it M. So if we substitute all that in our equation, we will get this monstrous equation. The sum of all the present values we wanted to obtain is all this formula, which we can reduce to a beautiful formula, which is this one over here. So here it is. This over here is a multiplier, a factor that you multiply the future values or the cash flows by to obtain the sum. So this is what I call the multiplier. You must multiply future value by this to obtain the sum. So this sum is then this multiplier by the future values or the cash flows. So my multiplier is then this. That's our next formula. My secret weapon for so many years. As you remember, the sum of all present values did not consider the initial investment. So what happens if this sum is equal to the initial investment? That means we are in break-even. So if we want to get break-even, we need to equal that sum to the initial investment. So if that sum is equal to the investment, then the initial investment, is the same that the multiplier times the future values, right? Okay, so also the multiplier is, clearing it out, is the initial investment divided by the future value. So what do we need this for? Let's go back to the formula. Imagine that we need to clear from this formula the n, the number of terms, and that we need to get the break-even. And do you remember from our last chapter what that number of periods meant? It meant the payback period, right? So if you clear this n from this equation, it's not easy, but also it's not that hard. We'll leave it for homework. I did it myself, and here is the formula. The logs can be in any base if both logs have the same base. So here's the formula. Then you have here the multiplier. That remember that if you have here the initial investment divided by the cash flow, then you can use that here as the end multiplier. So let's see an example of this. Okay, imagine that we have a loan of $10,000 and that we are paying, or we are able to pay $100 per month, and that the bank is charging me 10% as the interest rate. So I would like to know, for example, how many months will I pay the loan? That's a simple question, right? And this formula will help us a lot for that. Here, the multiplier then is, as I told you before, the initial investment divided by the cash flow. So the initial investment here is the $10,000 we're granted, and the future value then is the $100 we're paying per month. If we divide 10,000 by 100, our multiplier is then 100, right? So if we put 100 here and the 10% here, remember that we need to convert this to monthly rates, right? The 10% is in annual terms. So we need to convert it. And here is our formula, remember? So the 12th root of 1 plus the 10% minus 1, which if you calculate it, it's 0.7974% per month. Okay, so we have the interest, the monthly interest. We have the multiplier, which is 100, and let's calculate this number. Here's the logarithm of all this divided by the logarithm of this, and if you calculate that, you get 201 months. So that means you're paying double of what you borrow, and that is because that 10% is a very big interest rate. So the funny story is that I thought I had discovered the panacea of all formulas, because with this formula you would be able to calculate a lot of stuff without the need of complex spreadsheets to do sums and bring into present all cash flows, etc. You would just need like a table, like this one over here. See? For every discount rate here, or the interest rate, and the number of periods, you have the multiplier, where I highlighted the 100, 200 problem we just did. Of course, it's not precise because the number should be 100 exactly here to obtain the 201 months that are required to the loan to be paid. But with this table, you will have it all. Well, the funny thing, the formula I thought I had invented was already invented. 20 years later, when I'm making these videos, I did some research on Wikipedia and look what I found. In the time value of money chapter, they have present value of an annuity for end payment periods. And here is my multiplier. Of course, they don't call it multiplier. And of course, they haven't cleared the N for what I read. Our next formula is the internal rate of return. This formula is interesting because there is no formula for it. Well, what that means is that the IRR, the internal rate of return, cannot be clear from the formula where it derives from. Let me show you. As you recall from our last chapter, the internal rate of return is the discount rate at which the cash flows must be discounted or brought to present so as to obtain 0 when you add them all up. Okay, so here in our net present value equation, it would be this I in which instead of obtaining a number, we get a 0 here. So this is the equation. As you see, this is the internal rate of return that is impossible to be clear from it. But what computers do is that they make iterations so as to obtain a number that brings this equation to 0. Okay, our last formula has to do with the present value of a perpetuity. That is a project that has infinite number of cash flows. It is a project that goes on to eternity. It's a quick way for valuations of real estate and stuff. So what you do is that you assume that the number of months or the number of periods are infinity. I mean, you make the n go to infinity. When that happens, this term cancels out, so you have the present value of that perpetuity is actually the cash flow, the constant cash flow, divided by the interest rate. So, as I say, I assume that all my future values are constant from here to eternity, right? What happens if the cash flows are not constant? Because every project grows in the future. So imagine that your project, all the cash flows of your project grow in a particular percentage per year. Let's call it G, growth. Well, in that case, your perpetuity formula is this one. It's the same one, but you have to subtract the growth from the interest rate or the discount rate you are discounting your cash flows. Okay, our last formula is the profitability index. It is very simple. It's like the definition said, all the cash flows brought to present by their present value divided by the initial investment. Remember that we don't take into account the initial investment in the numerator. Is from the first cash flow to the M cash flow divided by the initial investment. So remember that if we have 1 here, or 100% as I call it, it means that our investment is the same as all the cash flows brought to present. Okay, enough for today. So we have all our formulas, all our tools to make our first business case. So please stay tuned for the next chapter. In our next chapter, we'll do a business case from scratch. Stay tuned. Don't forget to subscribe. See you in the next chapter.